Let me welcome you to this lecture. During this lecture, we will learn about the character table. I'm sure you have heard about uh, character tables, and in character tables, all the information that we need for working out different problems in chemistry by using symmetry or group theory are essentially listed together. And during this lecture, what we will see, what kind of informations are available within a character table and how we can possibly use these information in our exercises. So let's see what are the character tables. So there are several sections in the character table. We will see what are given in each of the sections and what are the significance of these information. So for example, let's take the character table of the C2B point group and then see what informations are present within this C2B point group character table. So the group symbol, that is the Sonnenfly symbol of the point group, is essentially written at the left hand top corner of all the character tables that you are going to come across. And then the symmetry operations or the elements of the group are written here in this top section over here. So for C2B point group, we know there are 4 symmetry operations, and all of these symmetry operations are in different classes. So when you write the symmetry operations, you club them into different classes. Then instead of writing all the symmetry operations, you write symmetry operations within one class. So for C2B point group, we write the symmetry operations. Then there are the characters of different irreducible representation are written in this middle section. We know that in case of C2B point group, there are 4 different classes, and that is why there are going to be 4 irreducible representations in the C2B point group, and the characters of these 4 irreducible representations are essentially written over here in this section. So the first irreducible representation is the totally symmetric representation, for which the characters for all the symmetry operations are essentially equal to +1. And the second one is this, while the third irreducible representation and the fourth irreducible representation is this one. So here are the irreducible representations of the C2B point group. Now to denote each of these irreducible representation, instead of writing comma 1, comma 2, comma 3, comma 4, there is a notation or there is a symbol to write denote these irreducible representations, and this symbol is known as the Mulliken symbol because R.S. Mulliken proposed these symbols, and there are a few simple rules to find out the Mulliken symbol for a particular irreducible representation, and we are going to learn the rules for writing Mulliken symbols for different irreducible representation now. So the first rule essentially states that for one-dimensional representation, you use a symbol either capital A or capital B. So for one-dimensional representation, symbol A or B. When do we use the symbol A and when do we have to use the symbol B, that we will learn a little later. So next, what we see is that for two-dimensional representation, you use a symbol capital E. Now you should note that this symbol, this capital E, which essentially represents a two-dimensional irreducible representation, is not the same E that we write over here, which is the identity operation, and this particular E is the symbol for identity operation, while we write E here as a Mulliken symbol. That means we have a two-dimensional irreducible representation, and if you have three-dimensional irreducible representation. These are uh, represented by the symbol capital T. So when you write A or B, we know that it's a one-dimensional representation. When we see that the symbol E is written for two-dimensional representation, and for three-dimensional representations, the notation capital T is used. Now, how do you distinguish between A and B is given by the second rule for Mulligan symbols. It says that those irreducible representation or those one-dimensional irreducible representations which are symmetric with respect to the uh, principal axis of symmetry, that is 1D representations symmetric with respect to Cn are denoted by the symbol A. So what do we mean by symmetric with respect to the proper axis of symmetry, or Cn, or the principal axis of symmetry to be specific, is that if we look at this, in case of the C2B point group, we see that all the representations are one-dimensional representations, and that is why we will have to use the symbol either A or B to denote these irreducible representations. Now the principal axis of symmetry in case of the C2B point group is the C2 axis of symmetry that we see, and there is no other axis of symmetry in case of the C2B point group. So we see whether the representation is symmetric or antisymmetric with respect to the principal axis, that is C2 in this case, by looking at the character of C2 operation in that particular irreducible representation. And for the first two irreducible representation, we see that the character of C2 operation are +1 and +1. So we say that the first two irreducible representation here are symmetric with respect to the C2 operation. And the third and fourth irreducible representation, we see the character of C2 operation for these irreducible representation are equal to -1 and -1. So we say that the third and fourth irreducible representation are antisymmetric with respect to the C2 symmetry operation over here. So for the first two irreducible representation, we use symbol A, and for the second, the third and the fourth irreducible representation, we use the symbols capital B. Now we see that there are two representations with symbols A, and there are two representations with symbol B and B here. So in order to distinguish between such representations which have the same symbols, what we need to have another way to distinguish them, and that is done, or that can be achieved by the third law, that Mulligan, for writing Mulligan symbols. It essentially says we will have to write a subscript for the symbols over here with the symbols over here, and that we can do by looking whether the representation is symmetric or antisymmetric with respect to the C2 axes which are perpendicular to the Cn. So symmetric with respect to C2 perpendicular to the Cn. Then you use a subscript 1 for those representations which are symmetric with respect to C2 axis perpendicular to the principal axis of symmetry. We use a subscript 1, while if it is antisymmetric, with respect to C2 perpendicular to the principal axis, then we use a subscript 2 to denote those irreducible representations. Now in case of C2B point group, we see that there is no C2 axis which are perpendicular to the principal axis of symmetry here, because the principal axis is C2 axis, and apart from that there are no other axis of symmetry, and there is no C2 axis perpendicular to the principal axis. In those cases where the C2 axis perpendicular to the Cn is absent, you look at instead of C2, or instead of looking whether the representation is symmetric with respect to C2 perpendicular to the Cn or not, you see whether it is symmetric with respect to a vertical plane of symmetry or not. So we will verify, or we will find out whether the representations are symmetric with respect to the sigma v xz plane of symmetry here, and then write the subscripts 1 and 2 in these irreducible representations. So when we do so, for the first irreducible representation, what we see that it is symmetric with respect to sigma v xz. So we use subscript 1 for this irreducible representation, while the second irreducible representation is antisymmetric with respect to sigma v xz here, and that is why we use subscript 2 to in case of the second irreducible representation. And when you go to the third irreducible representation, you see that there is a it is symmetric with respect to sigma v xz, so we write 1, and when we look at the fourth irreducible representation, it is antisymmetric with respect to the sigma v xz, and then we write subscript 2. So now we have 4 irreducible representations in C2V point group, and we have denoted all of these irreducible representations by using Mulliken symbols, and we know they are all different symbols for all the different irreducible representation, and we can understand when we say A1 representation, we know we are talking about which particular irreducible representation in C2V point group. So that is how one can use the Mulliken symbols to denote or find out the irreducible representations in a particular point group. So apart from this is the section where we write the Mulliken symbols, and there are 2 more sections in the character table. We will learn about these 2 sections or what is written in these 2 sections of the character table. But before that, let us go and learn more about these Mulliken symbols, because these rules are not enough to denote each of the irreducible representation in character tables where there are more number of irreducible representations. And then we again run into conflicts or duplicate symbols in those character tables. So for that purpose, a couple of more rules are required to distinguish between irreducible representations. And so we will look at character table of D3H point group to learn about these rules. So in case of D3H point group, there are 12 symmetry operations, and these symmetry operations are clubbed into 6 different classes. Let me write these symmetry classes and also the characters of different irreducible representations, so that we can write the Mulliken symbols for these irreducible representations. So there are 6 classes. There are going to be 6 irreducible representations in the D3H point group, and as we have learned already, that there is going to be a totally symmetric representation in each of the irreducible character table, or in case of each of the point groups. So the second irreducible representation is 1, 1, minus 1, 1, 1, minus 1. The third one is a 2-dimensional representation, and that is why the character of identity operation is equal to 2, minus 1, 0, 2, minus 1, 0. Then we have 1, 1, 1, minus 1, minus 1, minus 1. Then we have 1, 1, minus 1, minus 1, minus 1, and then plus 1. So we have another 2-dimensional representation, that is E, which is 2, minus 1, 0, minus 2, 1, 0. So let us try to write the Mulliken symbols for these irreducible representations. We know this is a 1-dimensional representation, and in this case the proper axis of symmetry, or the principal axis of symmetry, is the C3 axis, and there are C2 axes perpendicular to the C3 axis. So we will look also into that to write the Mulligan symbols. So the first one is going to be A because this is symmetric with respect to the principal axis, and since it is also symmetric with respect to the C2 axis perpendicular to the C3, so that is why we can write A1 here. And the second one is also A because it is symmetric with respect to C3 and it is anti-symmetric with respect to the C2 perpendicular to the C3, so it is an A2 notation we can write for this. So then the third representation is a two-dimensional representation, so we use the symbol E to denote this irreducible representation. Then we have the fourth irreducible representation, which is 1 plus 1 again plus 1. So this is also going to be A1, we see, and this is going to be equal to A2 because this is minus 1, this is plus 1, and this is again going to be E. So what we see again in case of the 3H point group, that there are duplicate Mulligan symbols for different irreducible representation, and this is not enough to distinguish between or to denote a specific irreducible representation in the 3H point group. So we need to use another rule for writing the Mulligan symbols, and this particular rule says that you can write a ref or double ref for a particular on top as a superscript on the Mulligan symbol by looking whether the representation is symmetric or anti-symmetric with respect to the sigma h which is present in the 3H point group. So we see that these two representations are symmetric with respect to the sigma h, while all the three are symmetric with respect to the sigma h, while these three are anti-symmetric with respect to the sigma h. And so symmetric representation we use single ref, and for anti-symmetric representation we use double ref on as a superscript on top of these notations. So that is how now we can distinguish between the irreducible representations in the 3H point groups or in point groups where we have a sigma h. When we look at whether the representation is symmetric with respect to sigma h, if it is, then we write single dash, and if it is anti-symmetric with respect to sigma h, we use double ref to denote that it is anti-symmetric with respect to the sigma h symmetry operation. So that is how we can distinguish or different symmetry or different irreducible representations in D3H point groups by writing different Mulligan symbols. But then again, in point groups where there is no sigma h, we cannot use this rule. So for example, in case of D and D point groups, we do not have horizontal plane of symmetry, and that is why we cannot write dash and double dash, and instead we have to write, in order to distinguish, we need to use a different rule, and we will write the character table of D3D and then see how we can distinguish or how we can write the Mulligan symbols for D3D. So we have again we see that there is no sigma h in D3D point group, and as like D3H, in this case also there are going to be 6 irreducible representations, 1 totally symmetric irreducible representations. Then we have one-dimensional representation. Then we have a two-dimensional representation. So these are the characters of different irreducible representations in the 3D point group, and let's try to write the molecular symbols for these irreducible representation. The first representation is one-dimensional representation, and it is symmetric with respect to the principal axis of symmetry, and it is symmetric with respect to the C2 axis perpendicular to the principal axis. So it is an A1 representation. Second one is going to be A2, you can see, and third representation is a two-dimensional representation, so we write E. The fourth one is again A1 representation. This is A2 representation, and this is E representation. Again, what we see, we have duplicate symbols, polygon symbols for the irreducible representations, and this we need to augment the symbols to distinguish individual irreducible representations in this case as well. And here we do not have sigma h, so we cannot write ref or wref in this case, and that is why we look at whether the representation is symmetric or anti-symmetric with respect to the center of inversion. If it is symmetric with respect to the center of inversion, then you write symbol subscript G after the numeral that we have written over here, and if it is anti-symmetric with respect to the inversion center, then you write subscript U after the numeral that you have in case of the symbol. So this particular representation we see is symmetric with respect to the inversion center, so we write it as A1G representation, and the second representation is also symmetric, so it is A2G we write. Here this is also the two-dimensional representation, that is plus 2 here, so it is symmetric with respect to the inversion center, so we write AG over here, and this particular representation is anti-symmetric with respect to the inversion center. So instead of G, now we write U, and this is now A1 U representation. This is going to be A2U representation, and this is EU representation, because this is also anti-symmetric with respect to the inversion center. So now we see that we are able to distinguish different irreducible representations in case of the 3D point group, and that is how the Mulligan symbols essentially are all individual, distinct Mulligan symbols are there to represent each of the irreducible representations in this point group. So that is how one can write Mulligan symbols for different irreducible representations, and these are the rules that we need to follow to write Mulligan symbol for different irreducible representation. So you should practice writing Mulligan symbols for different irreducible representation. So you can pick up a particular point group and then take the character table of that point group and then try to write the Mulligan symbols for different irreducible representations in that particular point group. So let us proceed further. We are done with the Mulligan symbol, writing the Mulligan symbols of irreducible representations, but we have not yet completed or looked at all the sections in the character table. So we will go back to the C2V point group and we will draw the character table. We will try to complete the character table of C2V point group. Once again, let's write the symmetry operations. So we have A1, A2, B1, B2 representations in the C2V point group. A1 is totally symmetric, A2 is anti-symmetric with respect to the sigma Vxz, B1 is anti-symmetric with respect to the principal axis but symmetric with respect to the sigma Vxz, and that is why I have to write like this. So this is B2 is anti-symmetric with respect to C2 as well as sigma Vxz, and this is what we have. So we are now familiar with this part of the character table. That is, we know where we write the symbol of the point group, where we write the symmetry operations as per their classes, the Mulliken symbols for different irreducible representations as well as the characters of different irreducible representations. Now, if you look at the character tables for different point groups in the that you have in any of the textbooks, these are given. You will see there are two more sections are written. That is, in this section, you write x, y, z, or Rx, Ry, and Rz against any particular irreducible representation, and in the last section you write quadratic functions against like x square, y square, z square, or xy, xz, uh, yz, as well as x square minus y square against different irreducible representations. So, how one can write that, we have already learned part of it. That is, we have seen earlier that we can take the x, y, and z coordinates as the basis, that is three-dimensional Cartesian coordinate as the basis in any of the point groups, and then we can see how these x, y, z axes go transform against each of these symmetry operations, and this allows us essentially to write a reducible representation by using this three-dimensional Cartesian coordinate as the basis. And when we find out the irreducible components of this reducible representation that we have done for the C3b point group in the last lecture, and we have seen that there are two irreducible representations we can get from this reducible representation that we have obtained, and these are one of the irreducible representation has characters +1, +1, and +1 for all the three symmetry operation classes, and the second irreducible representation is a two-dimensional representation, and that is the if you recollect the C3b point group. So it is 2e, 2c3, 3 sigma v, and the one we have obtained for which that is the z coordinate transforms as, for the z coordinate we got +1, +1, and +1, and what we have seen also that for x and y they are inseparable in case of the C3b point group, and the characters that we get for these is equal to 2 minus 1 0, and for this particular irreducible representation, this transforms as this particular irreducible representation. So this allows us this is how we can write or denote, or we can find out how these Cartesian coordinates transforms as different irreducible representation in any particular point group. So we will do this in case of the C2b point group as well, but we will use a different approach here. Instead of finding out the reducible representation by using the x, y, z coordinates as the basis, and then trying to find out the irreducible components of this reducible representation, we will use a different approach. You can of course use the same procedure as well that we have adopted for C3b point group, but here we will do it in a much more simplified way so that it is easy to understand for us. So let's take x, y, and z coordinates in this way. Now, in case of this C2b point group, we have an advantage, that is that all the irreducible representation here are one-dimensional representation. So that means here the x, y, and z coordinates are all separable from each other. Now, while it was not possible in case of the C3b point group, we have seen x and y were inseparable, and that is why they transform as a two-dimensional representation. But in this case, all the x, y, z coordinates must be separable from each other. Otherwise, if x and y are not separable or x and z are not separable, then they will transform as a two-dimensional representation, which is absent in case of the C2b point group. So we know beforehand that all of these coordinates are separable from each other. So what we can do is that we can take one of the representation here, or one of the coordinate as the basis, any one of them, and then find out the representation for that particular coordinate, and then we can match the characters of the representation that we obtained with any one of the irreducible representation, and then we can find out the coordinate transforms as which particular coordinate. So let's do that. Let's take the gamma z, or let's take the z coordinate as the basis only. So now we will find out the representation by taking only the z coordinate as the basis, and we will ignore x and y for the time being. So that is going to be gamma z for us. And then what we see is that if we do that for identity operation, it is going to be 1 because we have only one coordinate, and it does not change direction when we do identity operation. It is going to be +1. When we do C2 operation, it is along the C2 is along the z-axis. Z coordinate does not change, and that is why it is again going to be +1. And when we do sigma xz, we see once again the z coordinate is not going to change direction. It is once again going to be +1. And when we do sigma yz, again z coordinate does not change direction, and this is going to be +1. So what we see is that the z coordinate, the representation that we get by taking the z coordinate as the basis, these are the characters for that representation, and when we see over here, these characters match exactly with the characters of A1 irreducible representation. So what we can say is that the z coordinate transforms as A1 irreducible representation. So what we are going to write here, we are going to write z, and this tells us that z coordinate transforms as A1 irreducible representation in C2B point group. So now let's also find out for sigma x and gamma x and gamma y to find out how these coordinates transforms as. So when you do gamma x, only taking x coordinate as the basis, is going to be character for identity operation is going to be +1. Character for C2 is going to be equal to -1 because x will go to -x when we do C2 operation along the z-axis in this way. And then when we do sigma v xz, x is not going to change direction, so it is going to be +1. But when we do sigma v yz, then x will again go to -x, and this is going to be -1. So when we try to match the characters of the representation that we obtain by taking the x coordinate as the basis, that is 1, -1, 1, -1, it matches with the characters of V1 representation, 1, -1, 1, -1, as you can see. So now we can write x over here, and we know that x does transform as the V1 representation in the C2B point group. So if you do it for y coordinate again, you will find this is going to be -1, and when this is -1 and this is +1. So then we know that the y coordinate transforms as V2 irreducible representation. So this is how we find out how these coordinates x, y, and z transforms as in the C2B point group. We should also remember that these coordinates or these coordinates, the representation that we obtained by taking the translational modes of symmetry of any molecule in the C2B point group is going to be same as the representation that we obtained by taking the x, y, and z axis as the basis. So that means, what does it mean is that, so the translational mode of symmetry along the x-axis that we obtain has this particular symmetry again, because x transforms as V1 irreducible representation. We can also say that the translational mode of symmetry of the molecule also transforms as B1 representation, or the translational mode of symmetry along x direction has B1 symmetry, we can say. Similarly, we can say that the translational mode of symmetry along y direction has B2 symmetry, and translational mode of symmetry along the z-axis, z direction has A1 symmetry. So these also gives us the symmetry of different translational modes for any molecule in a particular point group. So then let us proceed further, because apart from x, y, and z, Rx, Ry, and Rz is also written in this particular section against the distinct irreducible representation. And how does one finds out where to write Rx, where to write Ry, and Rz? That is also very easy task for us, because what we can do is that we can take rotational vectors as the basis. So that is, these are the rotational vectors along the axis, because this rotational vector is along the x-axis. We denote it as Rx. This is along y-axis. This is Ry, and this is along z-axis. So we denote this rotational vector as Rz. Now we will see how these rotational vectors transform as under the C2B symmetry, and what we will do, we will again take gamma Rx. So how does the rotation, when we take the Rx, this rotational vector Rx as the basis, what representation we are going to obtain? That is what we are going to find out here. So when you do identity operation, of course the vector does not change direction, and we will have character equal to +1. Now when you do C2 symmetry operation, so C2 is along the z-axis, and this is your Rx, this is your z, this is your x vector. So this is your Rx. When you do C2 operation along the z-axis, that is rotating it by 180 degree, this vector will reach over here, and now it is going to be in this direction, because it has rotated 180 degree, and its direction is also going to get reversed. So what you have is the character for C2 operation when we take Rx as the basis is going to be equal to -1 over here. So then let's do sigma v xz. Sigma v xz is the plane which is lying on the plane of the board. So when we do that, again we will see that the vector will get, direction of the vector will get reversed when we do reflection with respect to sigma v xz plane, and that is why we will write once again -1 over here. And then sigma v yz, when we do, that is reflection on a plane which is perpendicular to the plane of the board, the vector will get simply reflected to this direction, but its direction is going to remain same, because we are reflecting on the plane perpendicular to this plane of the board, and that is why the character now is going to be equal to +1. So then let's see the characters of this representation matches with the characters of which irreducible representation, and then what we find that this is matching with B2 representation. So we write Rx against B2 irreducible representation. Similarly, if we do gamma Ry, we will find that this is +1 and this is -1, and this is going to be +1, because xz, when we do reflection with respect to xz, it is going to, the vector is not going to change direction, but when we do C2, it is going to change direction. And when we do reflection with respect to sigma v yz, it is going to change direction, and that is why it is going to be -1. So this is what is Ry is, we transform as B1 irreducible representation, and if we have gamma Rz, what we will find, it is +1. When you do C2, it is also +1 once again, because it does not change direction. When we do sigma xz, then it is going to be -1, and when we do sigma yz, again it is going to be -1, and that is why the Rz vector transforms as A2 irreducible representation. So that is how one can write the xyz or Rx, Ry, Rz transforms as which irreducible representation in any character table for different point groups. So then, in the last section, in the section over here, one writes how the quadratic functions transform as different irreducible representation, and that is where we write x square, y square, z square, xy, xz, and yz, as well as x square minus y square functions transform basis for which particular irreducible representation. So for this purpose, this can be simplified by taking the d orbitals as the basis. As we know, the d orbitals have the can be expressed by these quadratic functions, because we have d orbital. We know the shape of d orbitals for the z square, the x square minus y square, the yz, the xz, as well as the for the xy. So we can take these all of these d orbitals as the basis, and then find out the reducible representation for different for the d orbitals by taking the d orbitals as the basis, and then when you find out the irreducible components of these reducible representation, then you will be able to figure out where the different individual quadratic functions or individual d orbitals transforms as which particular irreducible representation. So now, in case of the C2B point group, of course, the task is much more simplified, because we know that each of the d orbitals here will transform as a one-dimensional irreducible representation, as all of these d orbitals are separable from each other, as they do not get mixed up, or their functions do not get mixed up when we do different symmetry operations under C2B point group. So we will take individual d orbitals, and then we will try to find out how does these d orbitals transform as in case of the C2B point group. So let's take the z square orbital. If we take, say, so gamma d z square, if we take, we know this is the z square orbital, this is x, this is z, and for the d orbitals have Gerard symmetry, that is, they have a center of inversion, and symmetry on both the lobes are essentially the same. So when we do that, so this is going to be plus 1, identity operation, plus 1, C2 is also going to be plus 1, sigma v xz is plus 1, sigma v yz is also going to be plus 1, because the symmetry does not change when we do different symmetry operation of C2B point group by taking this, the z square orbital as the basis. We get this as the representation, and that tells us that z square we can write over here, because the z square function transforms as a1 irreducible representation. Or we can also say that z square, dz square orbital, when we take the dz square orbital as the basis, we get a1 irreducible representation. So then we can also take the, say, xy. If we take, let's take the xy orbital. So that is, this is x, this is z, and xy is going to be if we consider that x and z axis lie on the plane of the board here, then the dxy orbital is the lobes of the dxy orbitals will lie on a plane perpendicular to the plane of this board. So then when we do the when we take the dxy orbital as the basis, so let's find out the representation. Identity operation is going to be plus 1 here, and then when we do C2 operation, we see that we will rotate it by 180 degree. This lobe will reach over here. Again, this one will reach over here, because they are exactly opposite to each other. So that is why what we will have, this also is going to be equal to plus 1, because symmetry of the lobes does not change when we do C2 symmetry operation. Then let's do sigma v xz. This is when we do reflection on the plane of the board, this lobe will move over here. So let's write it. What we will get, this lobe will move over here, this will reach over here. So what we will have is, similarly, these two lobes will get switched. So this is going to be the case. So the symmetry of the lobes have exactly reversed when we do the sigma v xz symmetry operation. So we write -1 over here, and when we do sigma v yz, that is reflection on a plane perpendicular to the plane of the board here. So this lobe will reach over here, this will reach over here, and again we see that the symmetry of the lobes switches or it gets reversed when we do sigma v yz operation. So then that is why we write -1 over here. So now we see that the A2, the xy orbital transforms as A2 symmetry operation, or the xy function transforms as A2 irreducible representation. So then let's also find out how does the xz, yz, and let's take the xz. So xz is, this is x, this is z, and this is what is the xz orbital. Now the orbital lies on the plane of the board. X and z axis also lies on the plane of the board here. And when we do, this is last one. So when we do C2, 180-degree rotation, this lobe will reach over here, this will reach over here. So the symmetry of the lobes gets reversed. -1 we have to write here. Sigma V xz is lies on the plane of the board. So the symmetry of the lobes does not change when we do sigma V xz. But when we do sigma V yz, it does change, and we have to write -1 here. So 1 minus 1, 1 minus 1, we know this is what is xz. So then let's also do sigma v yz. If we do, we write it in this way, but we know that the y-axis is perpendicular to the plane of the board, and that is why the lobes of these the yz orbital are also lying on a plane perpendicular to the plane of the board here. So then when we do that, this is going to be +1. When we do C2 symmetry operation, we know that this is going to be equal to -1, because the lobes are going to get, the symmetry of the lobes are going to get reversed. And when we do sigma v xz, again, this lobe is going to reach over here, this will reach over here, as we will do reflection on a plane which is perpendicular to the plane containing the lobes here, and that is why this is also going to be -1. But when we do sigma v yz, that is the plane containing the lobes of this the yz orbital, this is going to be equal to +1. So 1 minus 1 minus 1, 1. So this is what is yz function transforms as this B2 irreducible representation. So that is how we can find out how different quadratic functions transforms as in any particular irreducible representation. So this essentially brings us to the end of this lecture. And what we have learned during this lecture are the components, or the data, or the information that is present within a character table. We have seen there are 5 different sections in a particular character table. On the top left hand side corner, we write the point group symbol of the character table for that particular point group, and then we write here on the top the symmetry operations, or in class wise. So we club the symmetry operations in the same class and then write them. Not all the symmetry operations are written here, and then in here we write the Mulliken symbols for different irreducible representation. So we have also learned how, by looking at the characters of different irreducible representation, we can write the Mulliken symbols. There are 5 simple rules that we have to memorize, and this allows us to write the Mulliken symbols for different irreducible representation. So in this particular section, we write the characters of different irreducible representation. You have already learned how one can find out the characters of different irreducible representation by using the great orthogonality theorem. And in the last section over here, we write the different basis function, that is, we write with how the x, y, z, x coordinates transforms in case of that particular point group, as well as we also write how the quadratic functions like x square, y square, z square, xy, yz, and xz transforms in case of that particular irreducible representation. And we have also learned the procedure, how one can find out how these coordinates or the quadratic functions transforms as in any particular point group. So let me conclude this lecture with this, and I thank you for being with me during this lecture.